Hello everyone, welcome for this lecture. Today we are going to discuss the types of armature winding of a DC generator and EMF equation of the DC generator, and we'll solve one or two numericals on that. Okay, let's see first types of armature windings. As we said, the number of armature conductors are connected in a very specific manner. Okay, so very specific manner to give a armature winding. Okay, according to the way of connection of the conductors, the armature windings are of two types. Okay, one is lap winding, another one is wave winding. We'll see what is a lap winding and wave winding. Let's see the first one, lap winding. Here you remember, in this lap winding, the connections are overlap each other. Okay, like this. So we could have observed here. So this wave is overlapped. Okay, this is a continuous, like this. It is a overlapped one. Okay, like this it is overlapped. Okay, so this you can see in the diagram, right? Due to this, the number of parallel paths in which conductors are divided in is p. Okay, number of parallel paths will be p, therefore we'll say A is equal to p here. Okay, so the this one, like due to this, a large number of parallel paths indicate high current capacity of a machine. Okay, hence lap winding is preferred for high current DC, high current rating of a generators. Okay, so this is about lap winding. And then wave winding. In this wave winding, windings are travel ahead, avoiding the overlapping. Okay, there is you can observe, you have to draw both at a time. And since see, this is a black color with the one wave, means same wave, another one wave is moving like this. Due to this, it avoids the overlapping. Okay, due to this, the armature conductors always get divided into two parallel paths. Okay, how many made by, but those are all going to divide it by 2. Okay, therefore, so whatever we are going to take, parallel paths will be equal to 2. Okay, next, so we will see the difference between these two. In a lap winding, okay, in a lap winding, number of parallel paths, those are number of parallel paths will be equal to p, number of poles. Here, whereas here A is equal to 2, means number of parallel paths will be equal to 2 always, right? And then this is the first difference between these two. And the second one is number of brush sets required is equal to the number of poles. Okay, here brush sets will be equal to how many it requires is number of poles. Here number of brushes sets required is always equal to 2. Okay, so normal, this one is normally used. Okay, this one is normally used for a generators of a capacity more than 500 amperes, since it is a high current rating, so it requires high current, around high current rating generators we are going to use. Okay, and this one is preferred for the generators of a capacity less than the 500 amperes. Okay, so here total number of total conductors will be this will be number of z divided by p. Okay, so here the number of conductors will be, here number of conductors will be the total will be of divided by 2. Okay, means total conductors divided by here number of poles, and here divided by 2 in wave winding. Okay, I hope you have got these two. And then we'll move to EMF equation of a DC generator. To draw this, means to get a EMF equation of a DC generator, let us consider P is the number of poles of the generator. Okay, and phi is the flux produced by each pole in Webers. Okay, phi is the flux produced in each Webers, n is the speed of the armature, and z is the total number of armature conductors. Okay, a is the number of parallel paths in which in which the Z means total number of conductors are divided. Okay, so now as we have studied, A is equal to P, A is equal to P for your lap winding, and A is equal to 2 for wave winding. Okay, as we know the EMF, let's write the EMF equation. How it is induced? It is, as we have discussed, DC generator works on the principle of dynamically induced EMF. Okay, so that is according to Faraday's law of electromagnetic induction. Okay, we'll find out what is that. Faraday's laws of electromagnetic induction says EMF will be induced whenever there is a flux linking with a conductor. Okay, so in a very general words, if you would like to say, anyone, either if you have a, you should have a flux and you should have a conductor. If anyone moves, okay, if anyone moves and another one should be static, so then your EMF will be produced. Okay, so that is what we say, flux linking with a conductor produces an EMF. Okay, here it is dynamically induced EMF. Meaning of that one is conductor is moving and your flux field, whatever you say, electric field, is stationary. Okay, now we will write the average value of EMF induced in each armature conductor. Okay, we will take EMF equal to is the rate of change of flux. Okay, so E is equal to, you can say rate of change of flux, or you can say rate of cutting of the fluxes. Okay, cutting of the flux, that is given by, mathematically you can write this one as, okay, E is equal to d phi by dt. Let's find out what is the d phi and what is the dt. Okay, we'll find out that and then we'll start substituting the values of that one. Now let us consider only one revolution of a conductor. Okay, only one conductor and with only one revolution, means one complete cycle. Okay, in one revolution conductor will cut total flux produced by all the poles, that is means total uh, if a conductor, see, these are your north and south poles, this magnetic flux or it electric field. Okay, this is a conductor. Okay, if this conductor rotates complete one revolution, then a total, like, total flux produced by all the poles will be, like, phi into P. Okay, total flux into, and then it has crossed all the poles, so it is multiplied with the number of poles. Therefore change in flux, what we can say, is phi into P. Okay, then we need to calculate, means let us see what is the dt. Okay, how to do that one is, the time required to complete one revolution is 60 by n seconds. Okay, this much of time it is taking to complete one revolution. Okay, now then what we can write is dt will be equal to 60 by n. Since you know d phi, that is this one, and you know dt, then substitute these two values in this equation, that is E is equal to d phi by dt. Substitute d phi is phi into P, dt is 60 by n. Therefore n can move in the numerator, so 5 pn by 60. Remember, this is the induced EMF in a single conductor. That's what we have considered here. Okay, but there in the generator you would have a z number of conductors. Okay, with a number of parallel paths. Okay, so therefore when you have considered that, so total conductors will be z by a. Okay, based on your wave winding or a lap winding. Therefore total EMF will be E is equal to 5 pn by 60. It was already, we have got, it is for a single conductor. Now we have a number of conductors, therefore it will be z divided by a. So therefore your induced EMF of a DC generator will be equal to 5 z and p divided by 60 into a, when this is the EMF equation of the DC generator. Remember, A is the number of parallel paths. It may be, like, for a lap winding it will be A equal to P, for a wave winding it will be A equal to 2. Okay, hope it is clear. Now let's move to a numerical on this. Consider a 4-pole lap connected, okay, a 4-pole lap connected DC generator has a 600 armature conductor and runs at 1200 rpm. If the flux per pole is of 0.06 Weber, okay, 0.06 Weber, calculate the EMF induced Also find the speed at which it should be driven to produce the same EMF when wave connected. Okay, so we'll understand first the question and then we'll deal with this. Okay, observe this question. So first till this much. Okay, till this much you observe a 4 pole P they have given, it is 4 pole, and lap winding means A is equal to P, right? And then connected DC generator has 600 conductor armature conductors means Z is equal to 600, and then runs at a 1200 rpm, therefore it is N is equal to 1200 rpm, and the flux per pole is 0.06 Weber. So flux is 0.06 Weber. Therefore these are all the data they have specified, and till now I'm speaking about till now. Okay, so EMF. So what we can do is, we know that EMF induced EMF formula for a DC generator is equal to phi Z and P by 60A. Substitute, you know, phi they have given, the conductor they have given, speed they have given, poles they have given, 60 is a constant term, A also they have given. Take substitute all the values, we get a voltage. Okay, so now in the second term they have asked us to find the speed. Okay, we need to find out the speed at which, okay, at which it should be driven to produce the same EMF, means EMF remains same, and then connection will be like, you know, winding will be of wave connected. Okay, so now you can observe, this is the formula, EZ is equal to phi Z and P by 60A. In this, EZ remains same, that is 720. Okay, we need to calculate the speed, therefore N should be kept means like, you know, variable. So phi remains the same, conductors remains the same, P, and then 16 to 2, because 2 A equal to 2 we have taken, they have said that it is for wave connection. Okay, when you substitute, simplify, N you get as a 600 rpm. Okay, I hope you have got this, right? Let's see the second numerical, a bit different. A 4 pole, observe, a 4 pole generator with a wave wound has a 51 slots. Okay, so this has 51 slots they have given in terms of slots. Okay, so 51 slots are there, each having 24 conductors, means each slot having 24 conductor. Remember, then what about the total conductor? Total slots are how many? 51. Each slot, how many conductors it consists? 24 consists. Then what about the total conductors? It will be number of slots into number of conductors in that each slot. Okay, then 51 into 24 we have to do. Okay, this is about the Z. Only the difference is that one, they have not given directly Z total conductor, they have given in the form of slots and conductors per each slot. Okay, and then they have given flux per pole, that is 0.01 Weber at okay, at what speed must the armature rotate? Okay, they have asked us to calculate N. Okay, to give an induced EMF 220 volt. Now they have given voltage and flux Z. Okay, number of poles. Now we need to calculate what is the N. Since we know the formula, you can substitute and you will get that. Okay, we'll calculate that one. And the next, what they have asked is, other than this, they have asked what will be the voltage developed in the winding when the winding is lap. Okay, and the armature rotated at the same speed. Now they have asked in a second part, that is what will be the new voltage. Okay, what will be the new voltage produced when you have a when you have a lap winding. Okay, when you have a lap winding and armature rotation is same, say with the same speed. Okay, same speed. Let's calculate. I hope you have observed this. Let's calculate the numerical. What they have given, that number of poles are 4 and wave winding they have given wave winding, so A is equal to 2 to calculate speed. Okay, so wave winding, and then number of slots are 51. Each slot consists of 24 conductors, therefore total conductor will be number of slots into each conductor each slot conductors. Okay, that will be 1 2 2 4 comes. 5 they have given, easy they have given, N we need to calculate. Since we know that the formula is equal to phi Z and P by 60A. 5 you know, Z you know, N we need to calculate, P you know, 60, A you know. and even easy also, substitute all the values and then get what is the n comes 539.21. just calculate once and check. Okay, now we need to calculate what is the easy, that is EMF induced when with the same speed and the winding is lap winding. Okay, now we need to calculate what is the easy. We know this formula, easy is equal to 5 by 60a. Easy we need to calculate. Okay, so here 5 they have given, z also we know, n you have calculated, then p they have given, a is now lap winding, therefore a will be equal to p. Okay, so then if you substitute all the values, you get a easy is equal to 110 volts. Okay, I hope you understood this. Thank you.